Some background questions to ponder. If you drive 150 miles in 3 hours, what's your average speed? 50 miles per hour is your average rate of change. What's the generic math term for average rate of change? So slope of a line, oh, it's supposed to be moving here. There we go, equals average rate of change. Did you really drive 50 miles per hour constantly on your journey? No, that was your average rate of change. So let's fill in the blank. When driving, I looked at my speedometer and it read 65 miles per hour. At this instance, 65 miles per hour was my instantaneous rate of change. So in this lesson, we're going to be learning about average rate of change, and then you'll get introduced to instantaneous rate of change. If you leave at 1 p.m. to drive to Cincinnati, you arrive at 3:45, and note that your distance was 160 miles. What was your average speed? Right? So your rate is just the distance divided by the time. Right? So average speed is computed by dividing total distance traveled by total time elapsed. So if we divide 160 by, so the difference between 1 and 3:45 is 2 3/4 hours, or 2.75 hours. And if you divide those two, you get 58 miles per hour. Right? So average speed, just total distance divided by total time. So average rate of change, speed is the rate at which distance is changing over time. In general, average rate of change of a function over the interval of time is going to be average change in a quantity divided by total change in time. And this is a formula that we'll be using all year. Make sure it's in your notes. Right? Make sure you're filling your notes along with me. Right? So average rate of change, total change in quantity, any quantity, divided by total change in time, or total change in some x value. Right? So average rate of change, recall the formula for slope of a line through 2 points. And I wonder if my, oh, no, it's not here. All right, I'm going to grab my little arrow here. I lost him when I had to, there we go. Ooh, oh, here's a skinny arrow. And sorry, he's not pretty, oops, yellow like the other ones were. There we go. But now at least he's pointing the right direction. Ooh, there we go. All right, so slope is the change in y divided by the change in x. Right? Oops, did not mean to move that. Interestingly, there's a typo. So there, it's just fixed. I don't know if it was my typo or not. All right, so average rate of change. Right? So we're taking that, finding the value of our function at 2 different points and dividing by the change in x at those 2 different points, right? So it's the change in the value of the function divided by the change in x. Make sure you match it up so that this value of the function goes with this x, this value of the function goes with this x. All right, so here, if we wanted to find the average rate of change from here to here, this is just kind of blown up and put here. All right, we would take the difference in the y coordinates and then divide it by the difference in the x coordinates. All right, so for any function, we can determine the slope for 2 points on the graph. This is the average rate of change for the function on the interval from x1 to x2. And this is make sure this is in your notes. If it's not, secant. So secant crosses a curve twice. All right, so the average, and this is key idea here, which is why it's got a little asterisk. The average rate of change can be thought of as the slope of a secant line to a curve. Key idea there. All right, so we're finding the average rate of change. It was just like when you do in algebra 2, right? You found, oops, I'm going to get that to copy. There we go. Right, you found the slope of a line that connected to the 2 points. Right? So that line is crossing a curve twice, so it is a secant line. So average rate of change is the slope of a secant line to a curve. Right, so now let's look at this one. So consider y equals f of x equals x plus 1 squared. Find the rate of change in the y variable over the interval -1, 2. So we have to find the value of y when x is -1 and 2. Right, so we have f of -1. That's going to be -1 plus 1 squared. Well, that's just going to be 0. And then we have f of 2, which is 2 plus 1 squared, which is 3 squared, or 9. All right, so we're going to find our average rate. I'm not going to write slope, I'm going to write average rate of change. Okay, slope kind of conveys linear. Average rate of change does not have to be linear, and obviously this is not linear, it's quadratic. All right, so difference in the y coordinates, 9 minus 0. I just got to make sure I match them up. So 9 was 2, and 0 was -1. All right, so now, why does my -1 look like a 7? All right, so average rate of change is going to be 9 divided by 2 minus a -1, of course, is 3. So our average rate of change is 3. All right, so the average rate of change on the interval from -1 to 2 is going to be 3. Super easy, right? Super duper easy. Find the average rate of change of f of x equals 2x squared minus 3x plus 7 over the interval -2, 4. All right, so we've got to find the value of our function at -2 and 4. All right, so we have f of -2 equals 2. Actually, I'm not going to put that in parentheses. 2 times -2 squared minus 3 times -2 plus 7. Right, so f of -2 would be 2. So -2 squared is 4, and 4 times 2 is 8. And that's going to be minus a negative, so that's going to be plus 6 plus 7. All right, so that's going to be 14 plus 7, that'd be 21. And then f of 4 would be 2 times 4 squared minus 3 times 4 plus 7. So f of 4 is going to be 4 squared is 16 times 2 is 32 minus 12 plus 7. All right, so that's going to be 20 plus 7, that's going to be 27. All right, so our average rate of change, all right, it's going to be the difference in the values of the function divided by the difference in the x values. Whoops, I must have hit, I don't know how, expand the page. I'm going to go back and fix that because the sizing's all weird. So x2 minus x1. All right, so our average rate of change is going to be 27 minus 21. 27 goes with 4. 21 goes with a -2. So our average rate of change is going to be 6, and that would be 4 plus 2. So our average rate of change on that interval is 1. Okay, so the slope of the secant line here would be 1. All right, so here we have it already done. Here we're going to calculate the average rate of change. Remember, average rate of change is the slope of the secant line that connects the points. So this is the growth rate of fruit flies. All right, so the two values we're looking at are f of 23, which is 150, and f of 45, which is 340. To find the average rate of change, right, you would take the difference in the y coordinates, match it up with the appropriate x coordinates, and then simplify. So we have 190 divided by 22, but since we're talking about fruit flies, we might want to round to the nearest fly. So that's approximately 9 flies a day. Right, so that's the growth of our fruit flies in a controlled experiment here. So we have 9 more flies a day, which sounds pretty icky to me. So growing, here it is again solved out. So growing Drosophila, which is just fruit flies, in a laboratory. So we use the points P23 150 and Q 45 340. So these are flies And this is day. So that's day 23, day 45. I'm going to rewrite flies a little bit better. Right, so the y value is the number of flies. Right, so to find the average rate of change and the slope of the secant line, right, you've got 150 flies on day 23, 340 flies on day 45, increase of 340 minus 150 or 190 flies in 45 minus 23 or 22 days. So you take the change in the number of, in the population, number of flies, divided by the change in time. 340 minus 150, 45 minus 23, what gives you 190 over 22, which is approximately 8.6 flies per day. So that means about 9 flies per day. This average rate is also the slope of the secant line, PQ, right? And that's what you can see from the graph here. See our slope, here's our secant line. There's our secant line there, PQ. And it's just between these points here. Well, actually, it really doesn't make a difference because it's a line is going to continue with the same slope. But those are the points we used. All right, so this is a whiteboard practice. I'm going to skip by it. I'll post it. So I'm going to continue. It's only 11 minutes on my podcast here. All right, so average velocity. Let s equal s of t be the position function, where s is position in meters and t is the time in seconds. Right? So if we want to find our average velocity, we're going to take our change in position, which is our displacement, and divide it by the change in time. Right? So the change in displacement is just your change in position. Right? And you'll be given an equation, and that will tell you your position at and you'll use that to find your position at 2 different times. And your time is what you're given. Right? And make sure you don't forget your units. Right? So anytime we have any real world examples, make sure you use the units. So units divided by time. Like flies divided by days. Continuing on. So average velocity over the time interval t1, t2 is given by, so it's just the slope of the secant line. So it's going to be the change, S stands for position. So the change in position divided by the change in time. Right? And so it's basically just slope of the secant line. So the unit of measurement for velocities, meters per second, or unless it's some other unit of time, right? But it's always going to be the unit of measure, unit of distance divided by time. So for instance, actually, you know what? I'm going to get rid of this. I did, and I had an issue, and it didn't stay away. I'm going to do this myself. Cut. I had an issue with the board, had to restart, and so I didn't realize that. I restarted the whole computer. Didn't realize that was still there. So our rock is launched vertically upward. The height of the rock is given by s of t equals 100t minus 10t squared. Find the average velocity over the time interval of 1, 2. All right, so this is our position function right here. All right, so our position, we're going to find it at 2 different times. We're going to find it at 1 second, I believe. 1 second. All right, that would be 100 times 1 minus 10 times 1 squared, which gives us 100 minus 10, or 90. And then f of 2 would be 100 times 2 minus, no, okay. I almost thought I forgot the square, but it didn't matter for the 1. Huh? That's why it's just 10. So minus 10 times 2 squared. It's going to give us 200 minus, this will be 10 times 4, or 40, which is 160. All right, so our average velocity is just the change in position divided by the change in time. I'm just going to abbreviate AV. All right, so that's going to be 160 minus 90, and 160 goes with 2 seconds, and 90 goes with 1. So that's going to be 70 divided by 1, which is 70. I'm just going to assume it's meters per second because I don't see any other time any other units of measure there. All right, so 70 meters per second, that's our average velocity. All right, so notice that it's positive. All right, so positive velocity means that the rock is still traveling up. Let's do some more with velocity. So a student throws a book into the air and records the book's height as a function of time. Right? We want to find the average velocity of the book between half a second and 2.5 seconds. All right, so we don't have to plug it into anything because we already have our points there. So here's half a second, here's 2.5 seconds. So our average velocity, and I'll write out average velocity. All right, it's going to be the change in position versus change in time. Now I'll just abbreviate. Average velocity is going to be, so I'm going to use that larger number, 118.5 minus 44.5, and then 118.5 goes with 2.5. The 44.5 goes with 0.5. So our average velocity, if we subtract 118, it's late, so I'm going to grab a calculator. It's super late. I don't know if you can see the time on my watch, on my computer there. 118, oops. All right, so 118, oops. Net effect, it's so late, can't get the numbers in there. 118, of course this isn't a very good calculator either. 118.5 minus 44.5 is going to give us 74 divided by 2. I really could have done that in my head, couldn't I? It's like 11 minus 4 and 8 minus 4. Big deal, right? So that's going to be 37, and this is feet per second. All right, so the equation that best, oh, by the way, we're not going to do this one. Usually I have that one covered up. Oh wait, never mind. Wait, do I want to do that one? No. We may come back and do that another time, but now is not the time. All right, so what does this equation tell us? It tells us that the book is traveling up. We can come back, we'll come back and do that question a little later. I don't want this podcast to be too long. Right, so geometrically, actually I'm going to stop it. I think I'm going to stop my podcast actually right here, and then I'll pick up at this point in the next podcast. All right, bye for now.